So, as we began to learn more and more about the Earth, we had Wegener's idea that the continents or something was moving. He had no mechanism. Couple that with the advances of sonar to map the bottom, measurements of heat flow, and measurements or documentation of earthquakes and volcanic activity, then the revealing of deep earth layers from seismology made us start accepting that this evidence definitely suggests that there is seafloor spreading, that there is motion of pieces of the earth that we're calling lithosphere over the surface of the earth. A further strong bit of evidence came along about the same time, the whole idea of paleomagnetism. So a few key points. The earth has a magnetic field. It's why your compass points to the north. But you probably didn't know this, that a lot of rocks contain huge amounts of iron, particularly basalt. So the basalt that is all over that oceanic crust contains these magnetic minerals. They have iron in them, they react to the magnets, and as they cool, they align themselves with the Earth's magnetic field, which is shown in this picture here as the little flow lines. Notice they come out of the South Pole and they go through the atmosphere and through space and then re-enter the Earth about at the North Pole. That's this invisible magnetic field. The Earth behaves as a giant magnet. That's why they put that bar magnet in the middle of the Earth. The lavas that exude out of the Earth, wherever they're at, if it's basalt or some other lava that contains large amounts of iron, as it cools, it's going to feel that field and point in those various directions. Now, this magnetic field doesn't always stay this way. There is the normal situation. It's called normal because that's today, which is shown on the left there. Notice again the field lines emerge from the Earth near the South Pole and they go back in the Earth towards the North Pole. But we do know that there have been time periods in the geologic past, if we look at different rocks of different ages, where that has flipped and the Earth had a pattern of magnetic field that looked like the one on the right, which was what we call the reversed. In other words, the magnetic field lines emerge from around the North Pole, circumnavigate the globe, and re-enter the globe somewhere around the South Pole. This switches at irregular times. There's no true regularity to it, but it flips and flops back and forth. They don't always point north. We call this reversed polarity. We usually show it as beautiful, nice lines emerging from the south and going to the north, or the reversed. The reality is that even at best, shown here on the left, there's a little bit of slop to it, but you can still sort of see mostly an emergence in the south and a re-entering at the north. During time periods when there are switches or reversals, there's chaos. We don't know how long these reversals last or why they happen even, just the fact that they do. Now, if we look at the ocean floor and remember that this basalt that is coming out of this mid-ocean ridge, here's the Rift Valley for it, right in the center, if it comes out and that basalt cools, it's going to align itself. Either the little magnets within the rocks are going to either point north or point south. When we looked at the oceanic crust with these devices called magnetometers, it can measure the intensity of the magnetism of the rocks and then the direction. It revealed this very unusual pattern, which we show here as the different colors. Anything that has the color is normally magnetized, meaning it points to the north. Anything that has this light blue pattern, notice it points to the south. And look at the unusual pattern here. If you start at the mid-ocean ridge and either go east or west or left or right, depending on the orientation from it, you see stripes, sort of areas where the volcanic lava that came out pointed north because the field pointed north. But then places where it pointed south, north, south, north, south, north, south, north, south. And then if you look on the other side of these mid-ocean ridges, you get the exact same pattern. Same rocks, same polarity, same pointing north or south, and at the same age. This type of symmetry is remarkable, and it begged for a scientific explanation. So the next few slides just show how this may or may not happen. Here is this rising heat at a seafloor spreading center, and the lava that is just coming out today or recently is going to point north because we have a normal magnetic field now. Let a little time go by, and what happens? We have the rock that was pointing to the north, this blue pattern, about half of it gets spread, remember seafloor spreading, gets pushed off to the right, and half gets pushed to the left. Thus these big arrows here pointing in opposite directions. That'll become important next lecture. I'll talk about that in just a second. The new lava that's coming out after the Earth's magnetic field has switched is pointing the other direction. And if we let this go again, it's going to flip back again. And the same thing happens. About half of the material goes to the right side of the mid-ocean ridge and half goes to the left side and creates this stripy pattern. And so you can find all kinds of images in the textbooks and literature, and they always sort of show this stripy, this zebra stripy pattern. Never forget that they are beautiful, symmetrical pieces of real estate on either side of this mid-ocean ridge. The right side is the same as the left side as far as age, distance from the ridge, and then magnetic polarity. Summarizing it, we have these three basic facts. If lava is constantly erupting at those mid-ocean ridges, and that lava has magnetic minerals, and if the Earth's magnetic field sometimes points north, sometimes points south, the result is going to be that the cooled lavas are going to preserve this pattern of reversals if seafloor spreading is true. They do, and so we have verified that hypothesis. This diagram is a little bit more descriptive looking. So you see an early ocean basin, you see the rising heat, and then the different colors show the different sort of alignments. And you can also see the arrows pointing north, pointing south. And again, notice you get this nice tiger striping pattern on either side of this ocean basin. If we look at actual real data, here is data on the right side here, data from southwest of Iceland. Here's the mid-ocean ridge, the mid-Atlantic ridge in this case, and the different color patterns show the different rocks of the same age and same orientation. And notice the right side is the same as the left side. If we look at the Pacific coast, so this is the Pacific coast of California, Oregon, Washington, British Columbia, up to just near Alaska, you get a more complex pattern. It's been broken by faults, but you still see the tiger striping pattern that is symmetrical across these boundaries. This pattern is symmetrical across all of the mid-ocean ridges where we have found it. And so since about 1965, where this was presented in a series of papers and presentations around the world, almost all geologists have accepted that seafloor spreading is true. So the arc of our understanding is this. Continental drift, CD, yielded or led to the realization that seafloor spreading, SFS, was in a reality, which ultimately led us to what we call today plate tectonics. And plate tectonics can be summarized this way. The Earth's outermost layers, the lithosphere, which consists of the two crusts and the uppermost part of the mantle, they're hard and brittle, and they're broken into pieces that we conveniently call plates now. On this map you can see these lines sort of skirting through the ocean basins and along the edge of North America here. These are the broken pieces, these plates. How they move is that heat is constantly flowing up from our superheated cores, and that heat flowing up by convection is literally pushing these different plates around against each other and all over the surface of the Earth.